Welcome to the third video in a series of 6 about solving systems of equations in 3 variables. In this video, we focus on a solving method called addition and elimination. Here's an example. If you watched video 2, then you already know how to solve a system of equations like this using substitution. Nothing wrong with substitution. It works every single time. And the purpose of this video is to show you a different way in case you happen to like this better. What I do when I use the addition elimination method is I cancel the same variable 2 different ways. Let me be more specific about what I mean by this. What I do is I look at all the variables that have a coefficient of 1 or negative 1. You may recall we did the same thing in substitution, but for a different reason. And I randomly pick one of them. So for no particular reason, I'll choose the x in the first equation. Now, what do I mean by cancel the same variable 2 ways? I'm going to use that x with a coefficient of 1 as a means to cancel another x. So I'm going to choose the first 2 equations. I had to choose the first one because that was my chosen equation, but watch what I can do when I choose the second equation as well. I'm going to use the x in the first equation to cancel out the x in the second equation. So in order to do that, I'm going to multiply this top equation by 2. You might be wondering, why did he choose the number 2? Well, watch and you'll see why that was such a great choice. Because if I multiply the top equation by 2, which I've done here, and I leave the bottom equation alone, and then I add those 2 equations together, which you are allowed to do, then the x terms will cancel out. And so the multiplier of 2 that you see was chosen because in planning ahead, I realized that if I multiplied the top equation by 2 and then added the equations, that the x's would cancel out. So if you're wondering, why did I choose to cancel the x's and not the y's or z's? That's an arbitrary choice. You can cancel any letter you want as long as you cancel it twice, as you'll see as we go on here. And if you're wondering why I chose the top 2 equations and haven't done anything with the bottom one yet, that's also kind of arbitrary. Ultimately, you have to pick a letter and cancel it 2 different ways. How you do that is completely up to you. And each person will choose different paths when doing a problem like this using the addition-elimination method. By the way, they call it that because when you add equations, you eliminate a variable. The general theory here is this. You can multiply any equation by any number, and you can add any 2 equations you want together to get a new and valid equation. So there's more of an art than a science to this. One has to simply pick equations, multiply by numbers, and pre-plan well enough so that something cancels. All right, if you look at the equation at the bottom of the screen, you'll notice there's no x in it, so we're making progress. But I have to cancel the same variable 2 different ways. This was just canceling the x one way. So let's put that aside for the moment, and let's try to cancel x again, this time in a different way. Well, what if I were to choose the first and third equations? Couldn't I then use those 2 equations to cancel out the x? I could, and that's exactly what I'm going to do here. So I've taken the first and third equations, and I want to cancel the x here. Now you might be saying, well, couldn't we cancel the y or the z? Yes, but we already canceled the x once, remember? That work will reappear later. If we cancel the x the first time, I like to cancel the same variable another way. You'll see why that's beneficial as we proceed. So to go about canceling the x's here, it would be smart to multiply the top equation by -4. If you're not sure why I chose that, watch and you'll see why that was a good choice. Here I've multiplied the top equation by -4. I've left the bottom equation alone, and now you'll notice if I add my two equations together, the x's, once again, cancel. I'll pause while you verify the algebra mentally. So I've managed to cancel x's again. Look at the bottom equation on your screen. There's no x in that equation. Now remember, we've already gone through this once. There comes the work we erased earlier. And so essentially this is what the statement in purple means. We cancel the variable, the same variable, two different ways. It means I did some clever artistic algebra, caused the x to cancel. Then I did some different, very clever artsy algebra and got the x's to cancel again. So if at this point you're wondering, do we always have to cancel x twice? No, you can cancel y twice, or you can cancel z twice. It doesn't matter. I arbitrarily chose to cancel x twice. But now we're going to move on to a different phase of the problem. What we've done here is we've created a two-variable system of equations. Look at the two bottom equations on your screen. Here they are again. We've made a brand new system of equations here with two variables, using our original system with three variables. But what we do at this point is pretend like we're starting over on a brand new math problem. Now, I worked out this math problem on scratch paper, and I solved this two-variable system, and I got that y equals 3 and z equals -4. I did not show the algebra, and by the way, there was a lot of it. This was quite extensive. If you're not comfortable with those kinds of problems, you should either pause now and try to solve the two-variable system yourself and confirm that you do in fact have that skill. Or if you don't, I have a video called Systems of Equations in Two Variables that goes into great depth about how to go about a problem like this. So there's a lot that's not shown here because I'm trying to give you the bigger picture of a three-variable system. So after this tons of algebra that you can't see, we can now substitute the results we just got into any equation to find the missing variable. What do I mean by missing variable? That's the one we don't have yet, which is x. So I can plug my y and z values anywhere. For no particular reason, I chose this equation. And I can now plug in my y and z values that I solved from my two-variable system into that equation. And the rest is just very basic algebra. Hit pause if you want to analyze the particulars. But what this leads to is the value of x equals 1. And now that we know x is 1, and we had already found y and z, we now know x, y, and z, which is the final solution to this problem. I'm essentially done with this video. I would like to make a comment before we end. You may recall from video 2 and just in general about systems that there are three possibilities that can happen for the outcome of a system of equations. You can get one solution, which we did here. You can have no solution, which can happen, and you can have infinitely many solutions, the other possibility. The latter two, the no solutions and infinitely many solutions, are not covered specifically in this video. But I don't want you to get the impression, because they're not covered here, that by some magic, if you use the addition-elimination method, you don't get those two results. You can get them exactly the same way. And for more information on those kinds of systems, I refer you back to the three-variable systems of equations video, part 2 of 6. And that concludes this video.